Well, let's see. I'm reading over my PSK31 incoming information. The extra class students will do just fine on the test. Yeah, you heard it here first, right over the airwaves as well, from many operators wishing you the very best of success. Well, now let's take a look at transistors and that figure E6-1. What is the schematic symbol for a PNP transistor? Well, the way to tell is which way is the arrow pointing. If it's pointing in, it is PNP. If the arrow is not pointing in, it's NPN. So figure 1 is the PNP transistor. What term indicates the frequency at which a transistor grounded base current gain has decreased to 0.7 of the gain obtainable at 1 kilohertz? That's called the alpha cutoff frequency. Depletion mode field effect transistor, that's an FET that has a channel with no gate voltage applied. A current flows with 0 gate voltage. Now your handheld battery may become depleted if depletion mode FETs are used in many of the circuits. Even though there's no gate voltage applied, current is still flowing. That's the way to remember depletion mode. In figure E6-2, what is the schematic symbol for an N-channel dual gate? There's the key, dual gate MOSFET. And note that the arrow is pointing in, and there are now 2 gates, and that is answer B, showing figure number 4. I know you're ready to panic. Don't panic. Remember, only one question on your test will come out of this area. In figure E6-2, this is a different one. What is the schematic symbol for a P-channel junction field effect transistor? And that is answer A, figure 1. In the P-channel FET, the arrow is pointing out. For an N-channel FET, the arrow is always pointing in. So that's one way to identify that one. Why do many MOSFET devices have a built-in gate protective Zener diode? Well, that's to help us when we're working on circuitry. That is to prevent the gate insulation from being punctured by small static charges or excessive voltages. Be very careful when working with MOSFETs on the bench. What do the initials CMOS stand for? Complementary metal oxide semiconductor. That is metal, not mica, but metal oxide, and that is a semiconductor. Only one answer that has semiconductor in it for CMOS. How does DC input impedance on the gate of a field effect transistor compare with the DC input impedance of a bipolar transistor? Well, the FET has high input impedance. A bipolar transistor has low input impedance. Think bipolar, bipolar, low. Bipolar transistor has low input impedance. FET has high impedance. What 2 elements widely used in semiconductor devices exhibit both metallic and non-metallic characteristics? Well, that's silicon and germanium. Think of silicon rectifiers and germanium diodes. What type of semiconductor material contains fewer free electrons than pure germanium or silicon crystals? That would be P-type because there are more holes than electrons. It is a P-type semiconductor. And what are the major charge carriers in N-type semiconductor materials? Now remember, N-type, not P-type, but N-type would be free electrons. Finally, out of E6A17, 17 questions, only one of these will be on your test. Thank goodness. What are the 3 terminals of a field effect transistor? That is gate, drain, and source. Gosh darn semiconductors. Gate, drain, source, GDS. All right, let's now move on to other types of components found in the Gordo Magic Box. Oh, look at this one. This is a Zener diode. You see it? Yeah, looks like a Zener, doesn't it? Question E6B01. The characteristics of this little teeny Zener diode is a constant voltage under conditions of varying current. Man, that's neat. It always gives me a constant voltage even though the current may be going up and down and up and down. The principal characteristics of a tunnel diode is a negative resistance region. As a tunnel diode is conducting current, there is a spot where current increases as the voltage drop across the diode decreases. This is called the negative resistance region. That's a tunnel diode. Now remember, folks with tunnel vision are usually negative, so don't have tunnel vision. The question pool committee hopefully doesn't have tunnel vision when I tell them, come on folks, put all the right questions together as a group, not with something in between. So tunnel vision, negative resistance region. And that special diode capable of both amplification and oscillation is indeed the tunnel diode. Now, what type of semiconductor diode varies its internal capacitance as the voltage applied to its terminal varies? This is called the varactor diode, and we use these in VHF and UHF circuits by varying the voltage applied to the varactor diode. And looking at figure E6-3, the schematic symbol for the varactor diode is answer D, number 1. And remember, the internal capacitance of a varactor diode varies as the voltage applied to its terminal changes. Now, the varactor diode is a symbol that looks essentially a little bit like a capacitor and a diode combined. What is a common use of a hot carrier diode? Well, we use those as mixers and detectors. You want a real hot detector in your radio. Mixer and detectors as VHF and UHF circuits. What limits the maximum forward current rating in a junction diode? That is, how hot is it getting? Junction temperature, and that's what kills most junction diodes, is exceeding the temperature. Structurally, what are the two main categories of semiconductor diodes? Well, they're p-n junction and metal semiconductor junctions. p-n junction and metal semiconductor junction. Only one answer that begins with p-n junctions. What is a common use for a point contact diode? Well, we use those as detectors. The little point contact diode conducts in one direction, may be used as an RF detector in VHF and UHF equipment. What is the schematic symbol for a light-emitting diode? Well, it's a giveaway when you look at it. The light-emitting diode, abbreviated LED, looks like two little arrows indicating an illuminating device. And you'll see that on figure E6-3. Oh, there's no way I can remember all of these numbers and these diodes and these figures. Don't worry. On the last portion of this audio course, I'm going to go over and over and over again keywords that will refer questions to an obvious answer once you hear the keywords. So continue to hang in there. All right, now let's take a look at the voltage gain that we might get in a circuit E6-4. This is an operational amplifier circuit, and it's an easy formula. The formula is G, that is the gain, is equal to minus RF divided by R1. So it is simply RF divided by R1, or RF over R1. And they give you R1 at 10 ohms and RF at 470 ohms. This is not tough. 10 into 470 goes, that's right, 47. Now let's move ahead. How does the gain of a theoretically ideal op-amp vary with frequency? Well, that's a nice thing about the operational amplifier, the ideal one. It does not vary with frequency. Gain remains the same no matter where you are on whatever frequency. And in my book, I show you some great basics of the operational amplifier. What essentially determines the output impedance of a field effect transistor common source amplifier? Well, the resistance connected to the drain resistor, determines the output impedance of an FET common source amplifier. So the answer is drain resistor. And at the end of my course, I'm going to give you a great way to remember that, drain resistor. All right, now it's time to take out the calculator. Here's a new series of questions that they added to the question pool as of July of 2002. They say, what will be the voltage of the circuit shown in E6-4, that's the op-amp, if R1 is 1,000 ohms, RF is 10,000 ohms, and 0.23 volts is applied to the input. Now they want to know the voltage, not the gain, but the voltage this time. All right, the formula is voltage out divided by voltage in equals minus RF over R1. When R1 is 1,000 and RF is 10,000, we first calculate the gain, and the gain is minus 10. As a result, the output equals minus 10 times voltage in, which equals 10 times 0.23, or 2.3 volts. Now, remember, there are minus signs in front of it, and they will have an answer waiting for you, 2.3 volts. That's incorrect. The correct answer is minus 2.3 volts. Again, in my book, question E6B14, I show you the actual math. Remember, in this circuit, it is a minus voltage, and it's minus 2.3 volts. What is the gain? Oh, this is an easy one. Gain that can be expected from the op-amp when R1 is 1,800 ohms and RF is 68 kilo ohms, or 68,000 ohms. This is not tough. We're going to be dividing 1,800 ohms into 68,000 ohms, or taking 68,000 ohms divided by 1,800 ohms. Your calculator keystrokes are first 68000 divided by sign 1800 equal sign 37.777, rounded up to 38. And that's the answer. What voltage gain can be expected from the op-amp when R1 is 3,300 ohms and RF is 47 kilo ohms? Easy one. Divide the small number, 3,300, put it into the large number, 47,000, and you end up with 14.24. The answer on your test, 14.
You got all the stuff and the knowledge you can do that, so that's right.
Oh, that's great. We're tuned into FM, and they asked the question, E6B18, which of the following circuits may be used to recover audio from an FM voice signal? Well, not the double balanced mixer. Nope, it is a phase-locked loop. It's the PLL that we use to recover audio from an FM voice signal. What is the capture range of a phase-locked loop circuit? Well, that's a frequency range over which the circuit can lock. Now, for those of you with dual-band handhelds, chances are you've probably tried to receive well out of band, and that most handhelds will do that. But when you go so far out of the normal band that it's tuned for, all of a sudden the PLL will show unlock, or the letter U on the display. That means we have exceeded the capture range of the phase lock loop circuit. How are junction diodes rated? Now here we go back to diodes, a little out of place. Well, they are rated by their maximum forward current and peak inverse voltage. Maximum forward current, PIV. Common use for the pin diode. The pin diode is on and off. The pin diode acts as an RF switch. What type of bias is required for a light-emitting diode to produce luminescence? We always do the LED with forward bias. And the op-amp we talked about before, that's a high-gain, direct-coupled differential amplifier whose characteristics are determined by components external to the amp. And the term op-amp input offset voltage, that's the potential between the amplifier input terminals of the op-amp in a closed loop condition. Now, do you know the input impedance of a theoretically ideal op-amp? Input, think of high, H-I, and I-N. High N, very high. What about the output impedance of a theoretically ideal op-amp? Think of out with the letter O and the word low. So the output impedance is very low. The input is very high. H-I, each having the I in it, high and in, and low and out. That's how you remember the ideal op-amp. What is a phase-locked loop circuit? Well, that's an electronic servo loop consisting of phase detector, low-pass filter, and a voltage-controlled oscillator. Now, be careful. There's a couple of answers with VCO in them. It is phase detector, a low-pass filter, and the voltage-controlled oscillator. And what functions are performed by a phase-locked loop? Well, we do the phase-locked loop as a synthesizer in an FM transceiver. So a phase-locked loop function is frequency synthesis, only one answer that says that, FM demodulation. So frequency synthesis and FM demodulation. In my book, I talk a lot about phase-locked loop circuits, so be sure and read over that page, all about PLL. Now, speaking of L's, let's go to TTL from PLL. TTL, transistor logic circuits, E6C01. Do you remember the power supply voltage for a TTL series integrated circuit? Yep, TTLs work on not 12, but 5 volts. What logic state do the inputs of a TTL device assume if they are left open and it is high logic state? Now, input open, high state. Remember, 4 letters make up the word open and 4 letters make up the word high. So the input of a TTL device left open will have a high logic state. What levels of input voltage is high in a TTL operating with a 5-volt power supply? Well, high would be 2 to 5.5 volts. How about a low state in a TTL with a 5-volt supply? Well, low is way down there at 0 volts to 0.8 volts. That makes sense. What is not a major advantage of CMOS over other devices? Well, CMOS has a differential output. The CMOS circuit is small, consumes little power, but something not considered a major advantage of the CMOS is differential output. Now, the way you can remember this answer is, they say, what is not a major advantage? Their answers are small size. No, that is an advantage. Low power consumption, that is an advantage. Low cost, that is an advantage. Differential output is your only answer. That is a not answer. That is the correct answer. Why do CMOS digital integrated circuits have high immunity to noise on the input signal or power supply? Well, CMOS digital integrated circuits have the input switching threshold, which is about 1/2 the power supply voltage. Okay, I can tell by your eyes that you need a break. So let's go ahead and take a break. Not a vacation now, just a break. Go out there and feed the cat, feed the dog, water the horses, pet the pooches, and come on back. And by the way, when you're out there, snap a digital photo or two, because we love animals here at the Gordo household. In a few moments, we're going to be having our animals say hi to yours. We'd sure like to see what you have at your end of the radio circuit. And I'm WB6NOA at ARRL.com, and I'd love to hear from you. Okay, let's take a break, and then we'll start back at looking at AND gates and NOR gates. Question E6C07. Take a break. All right, we're back again with AND gates and NOR gates. Now, don't panic. Remember, out of all of these questions, E6C01 through E6C11, AND gates and NAND gates and TTL and CMOS, out of the C section, how many total questions could you have on your extra class test? Just one. So if we get to a brain thumper, don't worry about it. Go back just before the test or review the last portion of my audio course, and we'll show you how we make it easy. All right, let's take a look at E6C07, figure E6-5, and look at the AND gate. The AND gate looks a little bit like the letter D, doesn't it? The AND gate has two inputs or more and one output, but it looks a little bit like the letter D with two in and one out. In figure E6-5, what's the NAND gate, N-A-N-D gate, look like? Well, since the NAND gate has a logic 0 at its output, spot the little tiny 0 on its nose. Yep, there it is, and that is answer B, which is in the figure number 2. And again, looks like the letter D, the same as an AND gate except for the little circle at the nose. In figure E6-5, how about the OR gate? Well, the OR gate starts with the letter O, and its input is curved like a portion of the letter O. The OR gate symbol has a curved input and a pointed output. It is number 3 in your figure. How about the NOR gate? Well, since the NOR gate will give us a logic 0 at its output, if any inputs are logic 1, look for the little O on the nose. So the NAND with an N and the NOR with an N each have a little O on the nose and a concave input. It looks just like an OR gate except for the small circle on its nose that makes it a NOR gate. How about a NOT operation device, sometimes called an inverter? Well, the NOT gate is triangular in shape and has a little O on its nose. It looks altogether different from any of the other logic gates. You'll probably have the NOT gate maybe on your exam, and you spot it as figure 6, which is answer D. Looks a little bit like a triangle. All right, now let's go ahead and move into question E6D01. Much easier to understand and think about questions as you're zipping down the road or out there on the boat ride. In fact, we need to know where you're listening to these audio cassettes. So send me real photos to WB6NOA callbook address or email them to me. I want to see where you're doing your listening. How is the electron beam deflected in a Vidicon? Well, the Vidicom is an old type tube. I don't know why we still have this question in the pool. And the electron beam is deflected by varying electromagnetic fields in coils surrounding the tube, much like your TV set. The answer, by varying electromagnetic fields. What is cathode ray tube, CRT, persistence? Now this tells me for sure the question pool committee is living back there in the dark ages, because we haven't seen a CRT tube since my days with early marine radar and my very old days of working with slow scan television and an old SBE and robot SSTV decoder. Well, anyway, cathode ray tube persistence, even old oscilloscopes, I mean, they aren't around anymore. Well, anyway, the length of time the image remains on the screen after the beam is turned off is called CRT persistence. Wow, what an old question for a new exam. Now, if a cathode ray tube is designed to operate with an anode voltage of 25,000 volts, what happens if the anode voltage is increased to 35,000 volts? Yeah, you get that new TV set for your mom-in-law and you jack up the voltage from 25K to 35. The image size will get smaller and the tube will produce X-rays. This is not good. In fact, it's very important that you never transmit on your transmitter if your TV set is on an outside antenna and you see that TV picture shrink down to a little white dot on transmit. That's giving out X-rays more than likely, and it's probably going to damage the television. So on a CRT, if you have over voltage of the anode, it's going to produce X-rays. Not good. Exceeding the design rating can cause a cathode ray tube to generate X-rays, and that is the anode voltage. Okay, we're up to date now. Which of the following is true with a card chub? I'm sorry. I thought I'd leave that one in just to show you that I'm having as much fun doing these audio courses as you are by listening. That's one of the bloopers we'll leave in. All right, let's try that again. A charge coupled device, CCD. What's true about that other than I can't say it? Well, it samples an analog signal and passes it in stages from the input to the output. Charge coupled device. See, studying for extra class, this is a hobby radio license. We need to have a little bit of fun. And if you're not here in one of my live classes, you're going to enjoy some of my bloopers right here on audio. What function does a CCD serve in a modern video camera? Well, it stores photo energy. It stores photo generated. I got it. Here we go. The functions of a CCD serve to store photo-generated charges as signals corresponding to pixels. Now, the LCD, liquid crystal display, it is a display that uses a crystalline liquid to change the way that light is refracted back to you looking at the display. Now, many of you have new HF transceivers in your vehicle with a LCD display. You may find that if you wear dark glasses that are polarized, the display either looks great or it turns black. Well, oops, manufacturers of the ones that turn black when your head is held upright made a goof and their LCD is cross-polarized. But nonetheless, LCD displays are great to be seen in bright daylight. Now, it is common that the LCD display may slowly turn black temporarily when it gets real hot. So that's why if you have the LCD display on your dashboard, you might put a little towel over it to keep its temperature down so it doesn't temporarily turn black. It'll be okay after it cools down. Now let's take a look at toroidal inductors, because if you go mobile, you're probably going to use a lot of these inductors to help keep the RF out of your mic cord. What material property determines the inductance of a toroidal inductor with a 10-turn winding? I got it, 10-turn winding. Well, it is the core permeability and the material that it's made out of that determines the inductance. Now, by careful selection of core materials, over what frequency range can toroidal cores produce useful inductors? Well, this is neat. They go all the way from 100 hertz, I mean the bottom of the radio dial, to at least 1,000 megahertz. So 100 to 1,000 megahertz, and that is 100 hertz to 1,000 megahertz. Now, what is one important reason for using powdered iron toroids rather than ferrite toroids in an inductor? Well, powdered iron toroids generally have better temperature stability. What devices are commonly used as VHF and UHF parasitic suppressors at the input and output terminals of transistorized HF amplifiers? Now, if you've ever opened up some of those solid-state amplifiers, you see all those little toroid donuts around the input and output terminals of the transistor. Those are ferrite beads. And ferrite beads, boy, you got to have a handful of them when you go mobile, because they will help shield some of your radio circuits, including the microphone or your PSK31 or terminal node controller, from RF getting back into and causing distortion of your transmitted signal. What is the primary advantage of using toroidal core instead of solenoidal core in an inductor? Now think of a solenoid as a round like a Tootsie Roll, the toroidal like a donut. I'm getting hungry already. Toroidal cores contain most of the magnetic field within the core material. Almost nothing leaks out. How many turns will be required to produce a 1 millihenry inductor using a ferrite toroidal core that has an inductive index, that's A sub L, value of 523 millihenries for 1,000 turns? Now, here is the formula I'm about to give you to calculate the number of turns required to produce a specific inductance, where you know the inductance index A sub L of the material. A sub L is determined and published by the core manufacturer, and you'll see it inside the box, and it has an index that lists the microhenries of inductance per 1,000 turns, or millihenries of inductance per 1,000 turns of single layer wire on the core. All right, here comes the formula. N is equal to 1,000 times the square root of L divided by A sub L, where L is inductance in millihenries of core inductor. A sub L is inductance index per millihenries per 1,000 turns. So in our problem, we have N is equal to 1,000 times the square root of 1 over 523. 1 is the 1 millihenry, and the 523 is the A sub L value. Now, if you work that out, if you multiply 1,000 times the square root of 1 over 523, it comes out with a big long number of 1,000 times the square root of 0.001912, and you work that out, 1,000 times the square root of 19.12 times 10 to the 4, and that works all the way down to N is equal to 4.37 times 10 to the 1, or 43.7. You are going to be older than 43 years old when you calculate this all the way through your extra class test. On the turns required, answers are 2 turns, nope. 4 turns, nope. 229 turns, nope. 43 turns, that's about how old you'll be when you get through working all this out, is the correct answer. And when you think about it, 43 turns is about the normal that you see wrapped around some of these coils. Now, how many turns will be required to produce a 5 microhenry inductor using a powdered iron toroidal core that has an inductance index, that's A sub L, value of 4 microhenries divided by 100 turns? Well, this comes out 35 turns. Now, wrong answers are 141, 79, 13. This is 35, pretty close to 40 some. N in this problem equals 100 times the square root of L divided by A sub L, or N is equal to 100 times the square root of 5 over 40, or N is equal to 100 times the square root of 0.125, and if you work that out, it comes out 35.3. Now, only 2 questions out of the entire extra class pool on these two, and as long as you remember, you're going to be between 35 years old and 43 years old when you figure these out and start winding. That's one way to remember it. But in my book, I show you how to actually work these problems all the way out. What type of CRT deflection is better when high-frequency waves are to be displayed on the screen? Well, the cathode ray tube electrostatic deflection is better for high-frequency signals. Electrostatic deflection. Horizontal and vertical deflection plates, similar to capacitor plates, deflect the electron beam onto your television screen according to signal voltages applied to the plates. So it's electrostatic, which is not true of a CCD device. and that is it can be used as an analog to digital converter? No, that is not true. That's the correct answer. The CCD device does use a combination of analog and digital circuitry. It can be used to make an audio delay line. It samples and stores analog signals, but it can be used as an analog to digital, an A to D converter. No, the CCD does not do that. What's the big advantage of an LCD device? Oh, LCD, they consume low power. That's their big advantage, very low power. What is one important reason for using ferrite toroids rather than powdered iron toroids in an inductor? Ferrite toroids generally require fewer turns to produce a given inductance value. All right, not bad. You're doing great. Let's do a little bit more, and let's turn on the radio system here, play a little bit of radio, and we'll dial up our radio to one of the voice portions of the band, and let's go way up here to a single sideband and start picking up some conversations on it. Uh-oh. What's the problem there? That's right, wrong sideband. So let's switch over.
Any energy worth that
There
darn.
we are. For single sideband phone emission, what would be the bandwidth of a good crystal lattice bandpass filter? So for single sideband, let's tune somebody else up here in single sideband. You know what that is? Yep, that's slow scan television. You can tell I'm on the 20-meter band, can't you? I don't know how I got over the lower sideband, but up here on 20 meters, on single sideband, there we got somebody tuned in. About 2.1 kilohertz at minus 6 dB would be a great filter. Now, we can show you the difference between different filters. There's another filter. There's another filter. There's another filter. And that's too tight. So it gives you an idea that 2.1 kilohertz for single sideband would be a good crystal lattice bandpass filter. Now, if we went to go double sideband, well, there's still a little bit of double sideband up on the 10-meter band and some way down on 75 and 160 meters. We'd need a pretty wide bandpass filter, namely about 6 kilohertz at minus 6 dB for double sideband. And that crystal lattice filter is a filter with narrow bandwidth and steep skirts made using quartz crystals. That is narrow bandwidth, steep skirts. What technique is used to construct low-cost, high-performance crystal ladder filters? That's right, ladder, not lattice, but ladder filters. Well, we measure crystal frequencies and carefully select units with a frequency variation of less than 10% of the desired filter bandwidth. Only one answer that says 10%. Which of the following factors have the greatest effect in helping determine the bandwidth and response shape of a crystal ladder filter? Well, that is the relative frequencies of the individual crystals. Keyword, individual crystals. And piezoelectric effect, I got that one out, didn't I? Piezoelectric effect, that's the physical deformation of a crystal when you apply voltage to it. And what is the characteristic impedance of circuits in which MMICs are designed to work? Now, MMIC, a monolithic microwave integrated circuit, MMIC. The beauty of the MMIC is that it has a characteristic impedance of 50 ohms. Wow, we're starting right at life begins at 50. So think of 50 ohms as what your transceiver is looking for. 50 ohms, that is the characteristic impedance of circuits in which MMICs are designed to work. The noise figure of a monolithic microwave integrated circuit amplifier, approximately 3.5 to 6 dB. but they offer good gain from 8 dB to as high as 24 dB and higher, all the way up to 1,000 megahertz. So this 3.5 to 6 dB typical noise floor is acceptable. What type of amplifier device consists of a small pill-sized package with an input lead, an output lead, and 2 ground leads? That is the MMIC, Monolithic Microwave Integrated Circuit. And we use MMICs in microstrip construction when we are building an amplifier for the microwave bands, because we don't want any long leads on the MMIC. Finally, last couple of questions. How is the operating bias voltage supplied to an MMIC that uses 4 leads? Well, we do the bias through a resistor and RF choke connected to the amplifier output lead. The DC power into the MMIC is through a resistor, and the supply voltage that most MMICs work at is 12 volts. And the common packaging for inexpensive MMICs is a plastic package. Wow, we've covered a lot of materials, haven't we, in the last couple of hours with our course here. Well, let's just do a quick review. Remember, MMIC plastic packages, they work at 12 volts, DC in through a resistor. The bias voltage is through a resistor or RF choke. Microstrip construction for the MMIC. Noise figure 3.5 to 6 dB. They work at 50 ohms. Piezoelectric effect is the physical deformation of a crystal. 6 kilohertz for a double sideband filter. 2.1 kilohertz for a single sideband filter. LCD consume low power. CCDs, one thing they are not is they're not an analog to digital converter. CRT deflection is electrostatic. You're going to do just great on your upcoming examination. So what we want you to do now is to know how well you have done, because guess where we are? We're ready to take a look at subelement E7. Now we've already covered subelement E5. 9 test questions out of 9 groups on electrical principles. We've already covered subelement E6 circuit components, 5 exam questions out of 5 groups. Now we're going to look at practical circuits, and these are not that tough, and there's very little math involved. Practical circuits, digital logic, amplifiers, impedance matching, oscillators, modulators, digital frequency divider circuits, active audio filters. This is in our next section on, for those of you on cassette, your, let's see, 1, 2, 3, 4. This is your 5th, coming up is your 5th cassette. Right now we're on the 4th cassette, but your 5th cassette will have practical circuits starting you off. So go ahead and take a long break or a short vacation, pet the cats, hug the dogs, brush the horses, feed the rest of the animals around, and we will see you on the next audio cassette. If you're listening to us on a cassette course, take a well-deserved break, and we'll be back for question E7 category, all about practical circuits.
Brady was made in Germany, and guess how they reversed the big prop? It has one prop, and guess how they reversed it, Don?
I got to hear about this one, huh?
Correct me, Grady. They have to stop the engine, and then the engine is started again in reverse. That's how they reverse the prop, right, Grady? That's common.
Yeah, that makes sense. All right, see you in a few minutes, or a few hours, or not more than a day or so. Gordo, WB6NOA, clear.
A Mercy ship that came out of Germany. Now, this one, I think, came out of the East Coast there somewhere.